Good afternoon, all. I welcome you all for the third session, third day. I welcome our resource person, Dr. S. Kalyani, ma'am. Madam, welcome, ma'am.
Yes, ma'am. Welcome, ma'am. Good afternoon, ma'am.
Good afternoon, ma'am. Shall we continue, ma'am?
Yes, ma'am. Yes, ma'am.
Yes. Thank you, ma'am. Please proceed.
Okay. Okay. Ma'am, is the screen visible?
Yes, ma'am. Yes, it is visible.
Okay. Okay. Once again, good afternoon to all the participants for this Atal ACT FTP. So, morning we were discussing about the machine learning algorithm. What is machine learning? Why we need to go for machine learning? What is AI? And machine learning is a subset of AI, and various methods which we can adopt for the machine learning algorithms, the model building, what are the steps involved. So all that we were discussing. Now we will go in much detail about one of the algorithm which is called support vector machine. So the support vector machine, it was developed by the inventor called Vladimir Babkin. He has actually written a book on the support vector machine. It involves a lot of mathematics. The entire concept of support vector machine is based on quadratic programming. Okay, so it is one of the conventional optimization technique based on which the model is being built. So it is an optimization algorithm which is in the background of this SVM. So what he says is, if you possess a restricted amount of information for solving some problem, try to solve the problem directly and never solve. A more general one as an intermediate step, it is possible that the available information is sufficient for a direct solution, but it is insufficient for solving a more general intermediate problem. So a problem which is having lack of data, okay, such problems can be addressed using support vector machine, and it will give the generalization ability. That is the main advantage of SVM when compared to all other algorithms. So this SVM was invented by, as I already told, Vladimir Babkin, and it is one of the widely or many tools are available in machine learning. Like decision tree is one of the tool, and we have random forest. Like that, lot of algorithms are there. But the widely recommended tool is machine learning. So in the machine learning is SVM. There is the support vector machine for the process of data classification. Whenever we want to classify the data based upon certain characteristics, we can very well apply SVM as the tool. And it is one of the supervised learning method. It belongs to the category of supervised learning machine learning algorithm. Okay, and it will analyze the data properly and recognize the patterns also. Pattern is nothing but a collection of data, and it can be used not only for classification but also for regression, that is prediction. And how it basically works is, as we already discussed in the morning class, linearly separable and non-linearly separable. So the data points will be plotted and there will be a hyperplane. Suppose if it is a two-dimensional problem, you have a simple straight line separating class 1 and class 2 label. But if it is a three-dimensional problem, you will be having a vertical plane which will be separating all the three classes. So like that, depending upon the dimension of the problem, you have an optimal hyperplane separating the classes with maximum margin between the positive samples and the negative samples if it is going to be a binary classification problem. Suppose if it is going to be a multi-classification problem, assume you have C1, C2, C3, C4. So what if there are 3 classes instead of 2 classes, what the SVM does is it takes C1 as one category, C2 and C3 is clubbed. Okay, so it does all the permutation combinations. So first it will do C1 versus C2, C3. Then the reverse, C2 will be taken and it will be classified with respect to C1 and C3 and so on. And the output of all the 3 will be combined in such a way that at the end result, the user will be getting either a C1 or C2 or C3. Okay, so it is like in digital logic circuit, we will be studying about multiplexer. It is similar to that, two input together, it is combined and finally we get a single output. 2 outputs will be combined, finally we'll be getting a single output. It is similar to that. So performs a job of classification by constructing an n-dimensional hyperplane that optimally separates the data into 2 categories. There is class 1 as well as class 2. And the concept of SVM is very closely related to neural networks. So what is a basic concept of SVM if you see? It is a linear model for classification, although we call it as the problem may be a non-linear model, but this is going to be a linear model. The output of the SVM, which we see in the form of an equation, that is going to be a linear model. And it is applicable for both classification and regression, as I already told. However, it can solve both linear as well as non-linear problem and work very well for many practical problems, which is having the real-time scenario. So what is the idea of SVM? It is very simple. The entire SVM algorithm, it creates either a line or a hyperplane which separates the data into classes. So here you can see in this picture, this is a 2-dimensional problem. For simplicity, we have taken a 2-dimensional problem. So x1 is one feature, x2 is one feature. All the green dots belongs to class 1 and all the blue squares belongs to class 2. So in order to separate this green and blue, already we are having a straight line. Okay, but if a new sample is given to the algorithm, either it will be putting here or here depending upon the characteristic of that new sample. Either it will be labeled as label 1 or label 2. But it is always better to have a margin, as I already mentioned, it is always better to have a boundary rather than the set value alone. So this boundary will decide the this boundary is decided by the optimization algorithm, which will be run in the background of the SVM, that is the quadratic optimization. So there is a possibility for some dots to lie on this boundary in this red color place. Some dots will be, some green dots will be there. Some blue squares will be here. So those data points, see, among these data points, 1 or 2 data points will lie on the boundary. Similarly, among these green circles, 1 or 2 data points will lie on this boundary. So those data points which is lying exactly on the boundary of the SVM hyperplane, they are called support vectors. These, so here you can see. Okay, let me rub this and show you. So here you can see this green and this blue is called support vector. Okay, so this support vectors are the major vector which is going to decide on how the algorithm is going to work, and these support vectors they have their own weights. Okay, like how in neural network we have weights. Okay, so some of the, it is representing the entire data set. Morning I told you, in the entire class of 40 students, one student is representing the class, and we call him a student representative. Similarly, among all these green dots, this one green dot will be the representing. Similarly, one blue square. So these support vectors play a vital role in classification process. And if it is going to be a linear SVM, it just works by drawing a straight line between the 2 classes. So if it is linear SVM, where we are normally we don't use it for linear problems, we go only for non-linear problems. But however, it is applicable for linear problems as well, which is separated just by a straight line. Machine learning model that is able to generalize between 2 different classes if the set of labeled data is provided in the training set to the algorithm. So this is what is SVM. It is a model. It is able to generalize between 2 classes if you give a data set with labelings. Okay. And the main function of SVM is to check that for that hyperplane that is able to distinguish between the two classes. Okay, so how that hyperplane is working, that the design of the optimal hyperplane is the major crux of the SVM. This already we have seen. Okay. Can anybody answer this? What is the objective of SVM algorithm? Answers, please. Okay. Some of them are telling C. So just to read it, all the points are more or less similar. Only the n is different. In the first option, n is the number of features. Second option, n is the number of samples. Third option, n is the number of target variables. Somebody is telling B. Okay. So the dimension of the problem, if you see, so we are mentioning n dimensional space. The dimension of the problem itself means that features. How many features you have, that much will be the dimension of the problem. Okay, if you have only voltage and current as your parameter or attribute, it is a two-dimensional problem. If you have voltage, current, and speed, it is a three-dimensional problem. Okay, so here n always represents number of features. N cannot be samples because samples will be very huge in number, 100, 1000, 1 lakh, any number. But number of features will be constant. For example, I can, if I have a data of 100 cross 10, I will give it. Somebody is having a similar data of 1000 cross 10. So the 10 is, the column size is going to be constant, whereas the row size is going to vary depending upon the number of samples that has been collected. Okay, so the option B is not at all possible. Option C is number of target variables, that is nothing but the output. So based on the output, we don't decide the dimension, only based on input we decide. So number of input is nothing but number of features. Okay, so automatically the answer is answer A. Is it clear? Participants are able to understand the main objective of SVM algorithm? Can I proceed further? Because we are going much into detail, so let me know whether you understand it. Okay, thank you, ma'am, for your response. Now, here the main thing is we apply SVM for nonlinear problem, and it is more widely preferred for nonlinear problems. In that particular aspect, we have the concept of mapping, SVM mapping. So what does this SVM mapping does is, in the input space, your data points are highly nonlinear. That is, you cannot find a single boundary which is going to separate the black dots and the white dots, right? It is highly scattered and clumsy. So what we do is, first let us have a region of black dots separately and a region of white dots separately by applying a concept called mapping. So this mapping is in SVM, it is called as kernel mapping. It is like shell. Okay. By applying this mapping, which is also a mathematical equation, which I will present in my further slides. Sorry, I will present in my further slides. What is the formula used for this kernel mapping? Through this mapping, we move from one space which is called input space. In input space, the data points, they are plotted as it is in a raw manner. Okay. In feature space, based upon this mapping technique, we have another plot where the black dots and white dots are clearly separated. So this is called kernel mapping. So once that is done, and finally you will get a solution. This is called the optimal hyperplane, which is shown in the green color shaded part. Okay, once this optimal hyperplane is designed, that will be replicating in this way in the input space. This is your final solution. But this is the intermediate step, which is very important and which is the basic concept of SVM also. So it is not like input space to output space. It is input space to feature space and then back to the solution. In SVM, we have either linear or non-linear SVM. So linear SVM is very simple to understand. Already the data are linearly separable. What is linear SVM is, if the data points are already in this form, that is, in this form, there is no need for mapping at all. That means the type of SVM is called linear SVM. If the data points are in this form, then we go for non-linear SVM. So here it aims to construct the linear decision boundaries that explicitly separate data into different classes. So the decision boundary, by explicit, it is linear, and it is applicable for classifying the data set that are inherently linearly separable. By default itself, they are linearly separable. So that type of SVM is called linear SVM. In order to understand the concept of linear SVM, I am taking a two-dimensional problem with binary classification. Here we have feature 1 as x1 and feature 2 as x2, and the box as class 1 and the circle as the class 2. So here you can see there is a hyperplane dotted line with a boundary which is together called the optimal hyperplane, and these 2 points are called support vectors, as I already mentioned, and this line is called the margin of separation. Okay, and you know the equation of a straight line is something like y equal to mx plus c. So this is the called the equation of this optimal hyperplane. One is W transpose x plus b. W is nothing but the weight of the support vectors. B is a bias. X is your raw input data. So this boundary is called -1, and the other extreme boundary is called equal to 1. Okay. So SVM algorithm runs in such a way that you will be able to find the optimal value of W. So SVM would object when it will find the optimal value of W by undergoing an optimization algorithm. So this margin, you can see either it can be a small margin or it can be a large margin, but it is not preferred to go for large margin. If you go for large margin, more number of misclassification will occur. So the smaller the margin, more accurate the model is. So if we go for non-linear SVM, either it can be a hard margin or it can be a soft margin. What is hard margin? Hard margin is something like this. Very, very small margin. It is rigid. Okay, it is not flexible. What is soft margin? Soft margin is this second picture. So it is highly stretchable. It is flexible. So this is called the soft margin. So the first one is called hard margin and the second one is called soft margin. What is the main underlying mathematical equation behind the development of this hard margin SVM? So this d of x is called a decision boundary. So this is your decision boundary, what we call it as the fitness function. Okay, so W transpose x plus b is the equation. So that is what here it is given. W transpose x plus b is your decision boundary. So what is the constraint? Either it should be greater than or equal to 1 for class label 1. For class label -1, it should be less than or equal to -1. So for one class label, it should obey this equation. For another class label, it should obey this equation. So that is the constraints. So linear SVM is formulated as an optimization problem of maximizing the margin between the classes of separation to determine the weight vector and the bias B. So the output of your optimization algorithm is weight vector W and bias B. So what is the optimization function or the problem formulation? Minimize the weights of everything. That is Q of W means it's like an array, which is equal to half of W now. Why I put W squared is because it is a weight matrix, it will be having some rows and columns. So we will be taking it as the W norm squared is nothing but W transpose into W. Okay, so how much ever support vectors you have, that much amount weights will be there. Here there is only 2 support vectors, whereas if there are more support vectors, accordingly the weight matrix size will vary. So finally, this is our major objective, and we formulate the entire SVM problem as an optimization problem, but this is as the fitness function or optimization or objective function subject to this constraint. Okay, we are multiplying this here itself, because if you put 1 here, automatically this will become wx plus b. If we put -1 here, this minus can be carried over here. So therefore wx plus b. So both these constraints will be satisfied by means of this single equation. Okay. So here n is nothing but number of features. So the data points closest to the optimal separating hyperplane with the largest margin 2 by w norm are specified as support vectors. Okay, so what are support vectors? Support vectors are the data points which are very closest to the hyperplane. Hyperplane is here. So whichever points are very close to this hyperplane, they are called support vectors. So what is soft margin? So hard margin, it is very rigid. So your objective function is W transpose Y. Whereas in soft margin, along with W transpose Y, you have another term which is added, which is called the tolerance. So soft margin performs the task by first mapping the input data to a multidimensional feature space and then constructing an optimal hyperplane separating the classes with maximum margin. So here input space, feature space, and then we have again the input space. So here, along with this term half W transpose W, we have another term called sigma I equal to 1 to n epsilon I, where epsilon I is like the tolerance for each and every feature. C is some penalty parameter. Normally, when we combine two objective functions, we have a penalty parameter which will be added with it. It is similar to that. And your constraint is also modified in such a way that instead of 1 here, greater than or equal to 1, here it will be 1 minus that tolerance for that particular feature. Okay, so that is the thing. And here another thing is here directly x is given, because in hard margin directly the input space will be working and the support vectors will be decided based on the optimization algorithm results, and the output is driven. Whereas in soft margin you have mapping. Kernel mapping comes only in soft margin. So, which is widely preferred? Soft margin is only widely preferred, not the hard margin. Because in hard margin, it is very difficult to get the converged results. Okay, so people prefer soft margin SVM only when they go for application. In this case, instead of x, here it is x. Hope you see that. X means directly the data point. Here it is phi of xi. What is phi of xi? X is applied to a mapping function and x is converted to a value called phi of x. Okay, it is something like this. For example, phi of x is say e power x. In neural network, you have seen activation function. Hope you are aware of activation function. It is similar to that. So in activation function in neural network, you get a signal, and this activation function has some mathematical formula like y equal to f of x. So that formula will be applied here, and you will get a modified signal out of this neuron which is having that activation function. It is similar to that. So kernel mapping or SVM mapping is very much similar to the concept of activation function which we have in neural network. So this phi of xi is done through kernel mapping, and this is the concept of kernel mapping in SVM. You are having data points scattered here and there. So this is when we go for a two-dimensional plane, this is the hyperplane separating the red and green dots. It is very complex in low dimensions. But when it is mapped through kernel mapping and it is brought to a three-dimensional problem. So here we are able to find the vertical plane separating the red dots as well as the green dots. Okay, so this is more simple in case of higher dimensions. Okay, so this kernel mapping can be done through 4 methods. The very popular is the third one. Okay, so the first method is linear kernel. It's very simple. It is just like taking the transpose of one data point and multiplying with another data point. Okay, so the entire X is a matrix. Okay, See, assume X is a 100 cross 3 matrix, 1, 2, you have 100 samples and you have 3 features, voltage, current, speed. Okay, so what you do is you call the first data sample as X1, second as X2, X3, and so on. So X1 transpose into X2. So X1 transpose means it will be like here. So this row and the second row will be converted into a column, and you'll be multiplying element by element. So that will result in a single value. Okay, that is what is given here. I of xi comma xj is nothing but xi transpose into xj. So as a result, you are finding some other equivalent value for each and every value in this original data set. That is a meaning. Mapping is nothing but that is a meaning. Okay, converting into some other domain, like in signal processing and all, you do Fourier transform, all those things. That is what transformation. Similar to that only is mapping. Polynomial kernel, this is another method of doing kernel mapping. Here the equation is slightly different. So xi transpose plus xj plus 1 power d. So this d is user defined. D is the degree of the polynomial. It can be any value greater than 0, but do not use too much high value like 10 or 11. Restrict to either 2, 3 or 4. Okay. So only it is called as the polynomial kernel. Next, radial basis kernel, which is derived from the RBF network, which is already available in neural network. So the equation for this is e power minus gamma xi minus xj norm squared. Okay, why here it is given norm squared is because converting the absolute negative value even into positive value. Of course, in square itself, you will get all negative values will be converted to positive values. And this gamma is called RBF kernel parameter, so which is user defined. It is going to be user defined. So gamma is a positive parameter controlling the kernel speed. It is the speed of mapping. So this is only widely used kernel mapping equation. Sigmoid kernel is, this equation is used for sigmoid kernel, which is having tan h. Here also A and B are user defined parameters. So Amma, you can use any one type of this equation to do the kernel mapping. Any doubt up to this point? So far, whatever we have seen is binary SVM. What is SVM? What is the objective of SVM? It is to construct an optimal hyperplane separating the classes and the data points which lie very close to the optimal hyperplane. They are called support vectors. And SVM is basically formulated as an optimization problem. It can be either a hard margin or soft margin. In hard margin, you will not have the second term in the objective function. It is only optimizing the weights and the bias function. Whereas in soft margin, you will be having the tolerance which is given for each and every data point. That is for the support vectors. So extra you have one term, and accordingly the inequality constraint varies. So most commonly preferred is soft margin, and in soft margin there is another step called kernel mapping, which will map the data points from input space to feature space, and in feature space the soft margin algorithm works in such a way we are able to construct your optimal hyperplane. Are you able to understand after this? Can I proceed further? Okay, thank you. Now the next one is multi-class SVM. Okay, so what is this multi-class SVM? When you have more than one class label, as I told, C1, C2, C3, and etc. So in that you have two methods. One is called one versus all method, another is called one versus one method. So what is this one versus all method? First you construct K SVM model with class I against, I told you know, C1 versus C2, C3. Okay. Then C2 versus C1, C3. So ultimately you'll be having 3. Okay. C3 versus C1, C2. So how many classes are there? There are 3 classes. Accordingly, there will be 3 SVM models. Okay. This one 1, this one 2, this one 3. And then you apply a concept of winner takes all strategy. That is in which the classifier with the highest output function assigns the class label. Okay. So this is one SVM model, this is one model, and this one model. A new data point will be coming and hitting the model. It will be applied in all the three models, and whichever is giving the highest output, accordingly the class label will be decided either as C1, C2 or C3. So here for every SVM model, we have K quadratic programming problems, each of size L, to be solved. It is simple, but it is computationally expensive and not commonly preferred. So we don't prefer this. What is the second method? One versus one method. So here, instead of constructing 3, we construct k minus 1 by 2. Suppose if it is, we are having k equal to 3. So 3 into 3 minus 1 is 2. One minute. Okay, here only we are having 3 classes. Okay. Okay, here I think in the first method, OVA method, C1 will take 4 classes, then only we'll be able to understand. If it is 3 means both will be same. Suppose if it is 4 classes means C1 will be taken against all other classes. Okay, so C2, C3, C4. Similarly, C2 keeping C2 as constant, you will be comparing with all other classes. So this will be repeated a number of times. So the number of models here will be large, whereas number of models here will be less. So here, if we have k equal to 4, for example, 4 into 3 by 2. 4 into 3 by 2. So this will be 6. Whereas here, I think you'll be having around 9. Okay. So 2 into 3 is 6. So constructs k minus 1 by 2 binary classifiers with the training data of 2 classes alone. See here, it will take all other classes. Whereas here, at a time, it will take only 2 classes. There is a simple difference. Okay. So classification is performed by max bit voting strategy after each binary classifier. Everyone is treated as a binary classifier. Here it is not treated as a binary classifier. Here it is one class versus many classes. Here it is 1 versus 1. So that is what is given. 1 versus many classes. Here it is 1 versus 1. So every case is treated as a binary classifier, and the decision function assigns an instant, that is a new data point is assigned to a class having the largest number of votes. Okay, so only if we work this, we will be able to understand. So just you remember that 1 versus 1 method is highly preferred, and the classification is based on voting strategy, which is given the largest number of votes. So what is the design procedure of SVM? We have only 2 steps. First step is select the kernel. Normally selected kernel is RBF. Once you select the kernel, you have to choose the parameter. One parameter is C, another parameter is gamma. C is your penalty parameter, which is available in the objective function, which we have seen here. This is the parameter C, which is user defined. So that parameter need to be selected. Second is gamma, which is available in the kernel to control the speed of the mapping. Okay. So C is cost of penalty and gamma is kernel spread. So this influences the classification and this influences the partitioning in the feature space. So how we do this selection? Here also we can apply some optimization algorithm to select the optimal value of C and gamma, but simple traditional approaches called cross-validation approach. See, in the literature, it is assumed that C should take only these values. You cannot have C like 0.1, 0.2, okay? C should be in the range like this, 2 power minus 5, 2 power minus 3, and so on, 2 power minus 1, like that. Similarly, gamma should be only in this range. So this is being standard, okay? You can have any value among this subset in C, any value among this in gamma. So what you do is you just construct a matrix. Here you have all the C values. Here you have all the gamma values. Suppose if C is 2 power minus 5 and gamma is also 2 power minus 5, you can check the accuracy of the SVM algorithm. We can put the accuracy as 90%, 92%. So how many samples have been correctly classified? Like that, you have to fill this entire grid. So suppose if there are 10 values in C and 10 values in gamma, the matrix will be a 10 cross 10 matrix. So you'll be having 100 possibilities, 10 cross 10. Okay, and you in this matrix you find the maximum value where the maximum classification accuracy is there. Suppose the maximum classification accuracy is somewhere here. The corresponding C and the corresponding gamma is selected as the optimal C and gamma value in the design process. Okay, so this is called the grid search method. So in the and five-fold cross-validation is another technique. Either you can use the data samples as it is, or in order to make it even more accurate, if there are 100 data samples, what I will do is I will split into 20, 20, 20. So totally there will be a five-fold 20, 20, 20. So first 20 versus remaining, first 20 will be taken for testing. The remaining 80 will be taken for training. That is case 1. In case 2, the second 20 will be taken for testing. So we have 5 possible cases. In every case, you have an accuracy. You take the average of all the 5 and then put that single value here. That is called 5-fold cross-validation. If you don't do that and you take the entire 100 samples as it is called a single fold, one fold or a single fold cross-validation. So hope you understand this. And finally, after selecting the optimal value of C and gamma, you just have to feed it in the algorithm and the model will be designed and you can validate its performance. Any doubt in the design procedure? Hello? Can I move further? Okay. So this is the basic crux. If you remember this, that is enough. Other things and all in MATLAB, we have built-in functions itself. No need to worry about anything. Just to understand the, of course, this is a big thing. SVM concept itself, it involves a lot of mathematics. So if you really want to understand it more deeper and deeper, you have to go work with data points manually to understand it still better. But understand the concept clearly so that it will be useful when you apply for any problem. So these are the advantages of SVM. So it is having a very good maximization of generalization ability will be very high in SVM and compared to neural network. So here it is mentioned in neural network, the class boundaries change as initial weights change. SVM maximizes the margin of separation between classes, improving the generalization ability. So the work of SVM is in neural network, only the weights will be optimized. Here, the margin of the optimal hyperplane is maximized in such a way that the generalization ability is improved. And it doesn't have any local minima. It does not stuck at local minima. Whereas MLP means multi-layer perceptron, such neural networks may have numerous local minima, but SVM is formulated as a quadratic programming optimization problem and hence has only one global solution. So whatever you acquire through SVM, that is a single thing. Suppose in the neural network, if you run, every time your answer will be different because it will get stuck at various local minima. But SVM algorithm, you give the data points and you run even 10 times, 20 times, you'll get the same result. Okay, the same weights, the same hyperplane you'll be getting. So that is the advantage of another advantage of SVM. And it is robust to outliers. Neural networks are more robust to outliers, which needs to be removed from the outliers are nothing but the noise data or the data which does not fit in the model. Okay, the data which is not suitable for the application for which we have taken, those are called outliers. So neural networks are more robust outliers, but SVM, the outliers can be easily suppressed. Even if there are outliers in the data, we need not have to remove it. We can feed it directly. That will be taken care directly by the penalty parameter C. Okay, so these are the important advantages of SVM over neural network. And these are some of the websites which you can refer in order to build the SVM model for any given problem. So in my PhD work, I have used libSVM because I did PhD in the year 2007 to 10. During that period in MATLAB, we were not having a separate toolbox, but now we are having a wonderful toolbox in MATLAB. So that itself is sufficient for you to use and apply for your problem. Can you answer these questions, please? SVM can be used for? Yeah, many of them are giving C. Good. At least the basic thing is understood. So SVM can be used both for classification as well as regression, as I already mentioned. In SVM, if the number of input features is 2, then the hyperplane is how the hyperplane will be if only 2 features are there. Yeah, correct, ma'am. It is A. Okay, if there are 2 features, obviously there will be a straight line separating the data points of the 2 features. In SVM, we are looking to maximize the margin between the data points and the hyperplane. The loss function that helps maximize the margin is called, so although that has not been discussed in the session, so here you can understand this. The loss function that helps to maximize, the loss function is nothing but that C into sigma epsilon I, which we have mentioned, that is called the loss function. So that is called as Hinge loss, okay? Now we'll go for applications of SVM in power system problems. So first we can see SVM as a classification tool where and all we can apply in power system. Of course, there are a wide variety of applications, but a few prominent applications I'll mention here. First is fault detection and diagnosis. Okay, so fault detection and diagnosis will occur everywhere. Okay, in transmission line we can have. Okay, so in many places we can, even in substation, everywhere we can go for fault detection and diagnosis. So for wherever we have this problem of fault detection, we can go for SVM. And even in induction motor, one of the PhD scholar of our department, they have applied SVM. He has applied SVM to identify the type of fault occurring in an induction motor, whether it is a bearing fault or what type of fault is occurring in the induction motor. So that study has been carried out using the SVM as a classified tool. So healthy condition of equipment, you can monitor the whether it is safe or not safe, something like that. Okay, so the healthy condition of equipments can be monitored, especially equipments like transformer, high rated transformer, which is very costly, so that we can maintain it properly rather than leading to blackouts. Then security assessment and power system, which is as derived from the stability assessment. We all know what is stability. So more or less stability and security are same. So stability we take it only for a given data point, whereas security we analyze for number of data points and we say whether the system is insecure. You all have remember about the operating states of our system: normal, alert, then emergency, in extremis. So if a power system will be put it in a normal state if all the constraints are satisfied. So like that, there are different states. So I can call normal state and alert state as a secure state. I can call the emergency state as an insecure state. So whether the power system at the particular point of checking whether it is in the secure state or insecure state, such type of classification can be done. Power quality issues classification can be done, like whether it is a sag, swell, which type of power quality issue has occurred based upon the data points. We can classify. There are some 5 or 6 power quality issues: flicker, sag, swell, harmonics. So what type of issue has occurred, that can be identified. And SVM as a regression tool, prediction. So prediction, normally we think of load forecasting. So for load forecasting, SVM is a very wonderful tool. It can be used as a time series regression problem. And similarly, power prediction from renewable energy source, it may be solar, it may be wind, or it may be a hybrid renewable energy system, hydropower, anything. So output power prediction can be done. What will be the output power produced from this system next month or the next year? Like that, power prediction can be done. So the actual session here is SVM and fault diagnosis. It is basically a research work. So I'll just try to address a few important points related to this one particular application so that you can apply this for any of the power system or any other problem which you come across. So in order to explain about the application of SVM in fault diagnosis, I have referred a paper which has been published by Professor Tukaram, who is a professor in IIC Bangalore. So he, along with his researchers, they have published in the year 2008 itself, application of support vector mission for fault diagnosis in power transmission system, which is published in IET generation, transmission and distribution. So what he addresses in this paper is he has used SVM for the post fault. It is not pre-fault, it is the post fault. That is, fault has occurred. Now they are troubleshooting how the fault has occurred. Okay, so it is a post-fault diagnosis purpose. SVM as intelligent tool. SVM has been used as an intelligent tool for identifying the faulted line that is emanating from a substation and finding the distance from the substation. Okay, so there some fault has occurred. They want to find due to which is the faulted line, which is the faulted line coming from the substation, or which line coming from the substation has been subjected to fault. So they need to identify that. Okay, each line will be given a line number. So they have to identify which line. And also finding the distance of the fault from the substation. Okay, so these two, for identifying these two, both the distance as well as line of fault, they have used SVM as an intelligent tool. And the approach described in this paper uses phasor values of the line voltages and currents after the fault has been detected. Okay. So how they are able to identify the faulted line and the distance? What are the input parameters? They are using the voltage and current. That is post-fault voltage and post-fault current phasor values. That is, if there is a three-phase system, VA, VB, VC, IA, IB, IC. The approach is particularly important for post-fault diagnosis of any mal-operation of relays following a disturbance in the neighboring line connected to the same substation. Although the fault has occurred and the consequences have happened, only if we do the post-fault diagnosis, we can see which relay has not performed its function properly and how the other subsequent lines have got affected. So this is the work which was proposed by Professor Tukaram and his team. So here there is a monitoring center which is called the Energy Control Center. So there are 4 substations. The 4 substations are completely monitored in this Energy Control Center. So we are able to track the voltages and currents at the point of substation, and that is given as input to the SVM, and SVM algorithm will be checked in the Energy Control Center. The output of this is the simple block. And here you can see for one particular SVM. Okay, so here this is the local information during the fault. What are the post fault voltages and currents? Those informations will be fed to the SVM model, and SVM will be identifying the faulted line as well as the fault distance from the substation. So these two are the output of the SVM, and this is the single substation. So there are 4 substations. They are taking one sample case and they are showing it in detail. Okay, so this is the substation which is subjected to diagnosis using SVM. So here you can see a more detailed description he has given here. Three-phase voltages at the substation, as I already mentioned, the input to the SVM is nothing but phasor voltages and phasor currents. So the three-phase voltages at the point of substation and the three-phase fault currents in the line connected to the substation. What are the various transmission lines connected to the substation? In all the lines, we are taking the fault current. So this is the substation voltage, and this is the fault current of line 1, line 2, line etc. up to line L. So this is given to the feature vector. So here, if needed, we can apply the feature selection algorithm to reduce the number of features. Else, directly we can apply the n-dimensional problem to the SVM model. So here both is done, both classification and regression is done. The classification is done in order to identify the faulted line number if the line belongs to the substation under diagnosis or it belongs to some other zone. See, under diagnosis means the substation has its own zone where it will be acted by relays and circuit breakers. Okay, so whether the faulted line comes under the purview of that particular substation or it comes under some other zone. So that will be identified through the SVM classifier model. Suppose if it is being identified that yes, the faulted line is within the zone of the substation, then the SVM regression model will identify using the same input parameters, it will identify the distance of the fault from the substation. That is, it will predict the distance of the fault from the substation. So here, what is the size of the feature vector? 3 is for voltage, VA, VB, VC. A number of lines is L. For each line, you have 3 phase values, IA, IB, IC. So the total dimension of the problem is 3 plus 3 star L. If there is 4 lines in the system, it is 3 plus 3 plus 3 into 4. So it is 15 dimension problem. So SVM design, how it is designed. Architecture of the SVM-C model and architecture of the support vector regression model. So this is for fault line identification. This is for identification of fault location on the line. So the input parameters are same as I already mentioned. VABC, I line 1 phase currents, line 2 phase currents, and so on. It will go on. So this is your feature vector. Okay. And so this SVM1 will identify the type of fault first, whether it is a symmetrical fault or unsymmetrical fault, three-phase fault, single line to ground fault, line to line fault, and double line to ground fault. And that in turn will be given to a number of SVMs. So SVM2, each SVM has been designed for one type of fault. Okay, three-phase fault or SLG fault. So all the data sets will be fed in such a way that if it is going to, if it is a three-phase fault, it will directly go to the SVM2. If it is a SLG fault, it will go to SVM3. Accordingly, the network architecture will vary depending upon the type of fault, because this is a balanced fault, whereas the other three are unbalanced faults. So first the trigger will be given to the type of SVM, and this SVM will finally identify the fault line. This is for regression. For regression also the input is going to be same. Here also the type of fault will be identified, either three-phase, single line to ground, line to line, and double line to ground. Accordingly, there are for each and every type of fault you have a model, and that model will be triggered depending upon the type of fault, and that model will give you the resulting fault location. Any doubt after this? Hello? Are you able to understand, participants, how the SVM model is used as a classifier and regression?
Madam, very well presented, very good night.
Thank you, sir. Now there is a quiz. SVM can be used for, I think this already we have completed. Yeah. So before I close off, I will give you a hands-on training, and I just wanted to show you a small video related to the SVM algorithm for you to have a better understanding. Okay, please hold on for a minute. And I have 2 journal papers, which also I will share to the coordinator. Madam can circulate. So this is the paper which I have referred for fault diagnosis and power system. If you read this paper completely, you will be able to get a much better understanding. I have just given the nutshell of this paper. But if you are really interested to, so this is the thing which, as they say, they have used soft margin. So what I want to mention here is, in all the real-time applications, only soft margin SVM is used, not a hard margin. Okay, because
Madam, can you show the title of the paper?
yeah, application of support vector missions for fault
IISc Bangalore,
diagnosis.
yes, madam.
IISc Bangalore, Tukaram. So this is the paper from which I have taken the content for presentation. Although I have worked in power system security assessment in detail in SVM, since the topic was given as fault and diagnosis, I have taken this paper, and they have applied this particular algorithm to a New England 39 bus system, which is a very popular IEEE benchmark system, and they have inspected it. They have also taken the various details of training and testing pattern, what are the line numbers, and they have taken the substation as bus number 16. And based on that, they have worked. So if you really go through this paper, and if you have any doubt also, you just put a mail to me. Whatever I know, I will try to reply to you. Because I have worked in this, although for this problem I have not worked, I work for some other problem, but to some knowledge, I can help you. So this is one paper which I will share with the coordinator, and another paper, it is a very simple paper which I got it from the ResearchGate. So this is the power system applications of support vector mission in classification and regression. So they are just giving the what to say, an overview of where and all SVM can be applied. Okay, how the concept of whatever we have seen, no, input space, feature space. In input space, it is highly non-linearly separable. Here, it is linearly separable, and the corresponding equation everywhere you can see the same equation what we have seen in the slides. So it is simple mathematics, and yeah, and how support vector regression is working. That concept is also mathematically it is given. At the same time, with application, SVC, there is support vector classifier in transmission line fault classification. So here they have just, as I already mentioned in the previous example, they'll be classifying the type of fault, whether it is a three-phase fault, line-to-line fault, or double line-to-ground fault, based upon the post-fault information. So this is the case study they have taken, and they have worked on it. And the accuracy is also given. Here you can see that RBF kernel, it is the common kernel mapping which is used. And for regression, they have used the load forecast. So one tool for classification is fault detection for type of fault, identifying the type of fault in a transmission line. And for regression, they have used load forecast. So this is the example. So you can just go through these two papers to have a little bit of more understanding with application idea. Okay. So now let us play a video, and let me know whether the audio is, whether you are able to hear the audio of the video. Can anyone reply? Whether the audio is also, you are able to listen? No. Okay, you just, I will play the video. I will explain it in a nutshell also. You just see the video alone. So in the first, example, he told that the two classes, they are separated by a hyperplane. Okay, but however, there can be number of hyperplanes separating the two classes. So in the second picture, he is showing two possible cases. One is green hyperplane, another one is red hyperplane. However, among the green and red, which will be the best, that depends upon the maximum margin. So here you can see Z2 is higher than Z1. So this G of X is called the decision boundary, which is separating class 1 and class 2. So this decision boundary, as I already mentioned, the formula is W transpose X plus W naught. W naught is the bias values, and W is the weights for each and every data point. If there are, say for example, 100 samples, accordingly you'll be having 100 weights. Okay, so when the decision boundary value is greater than 1, it belongs to 1 plus. If it is less than or equal to -1, it belongs to another class. Between 1 and -1 is called margin. Okay. So in the previous figure, you have seen 1 by W norm, and that is for one class label, the separation. The another class label also has 1 by W norm. So totally the objective function comes to 2 by W norm. So we are going to minimize 2 by W norm equation in such a way that the separation will be maximized. And the basic mathematics behind this is Karush-Kun-Takur. There is KKT conditions, which is solved using Lagrangian multipliers. Of course, I am also not that much good in mathematics. Anyhow, we'll just see the example. So here what he is doing is he is taking 3 points and they are going to separate a hyperplane between 1 comma 1 and 2 comma 3. So in order to have a hyperplane separating, assuming this is as class level 1 and class level 2, they are just joining these 2 points. If you join these 2 points, it will come here somewhere here. Okay, just he is taking the subtraction of 2 comma 3 minus 1 comma 1, and accordingly he is drawing this green line. So ultimately, in general, it is nothing but 1 comma 2, because 2 minus 1 is 1, 3 minus 1 is 2. So he is taking the coefficient as 1 comma 2 is taken as a comma 2a. Okay, there is coefficient here is 1, here the coefficient is 2, a is some real time value. So accordingly, the first equation for this 1 comma 1 will be a plus 2a. And you know that the equation is W naught will be added because W naught is the bias. Now for this 2 comma 3, the equation is 2 into A plus 3 into 2A. 3 into 2A is nothing but 6A. So just apply this point to this one. Okay. So 2a plus 6a plus w naught equal to 1. Why here it is minus 1? Because it is below the hyperplane. Why here it is 1? Because it is above the hyperplane. So accordingly, from this he has derived some mathematical analysis, and he has found the value of a as 2 by 5. Okay, and then by some substitution 1 minus 8a, here substitute the value of a which has been found in this particular equation, and finally the value of w naught, which is the bias, is being identified, and the w norm is taken as 2 by 5 comma 4 by 5. He has worked out. Only after working out we can arrive at this formula, and finally the decision boundary is this coefficient at x1 plus 4 by 5 into x2 minus the bias, plus the bias. Bias is nothing but minus 11 by 5. So 5 is common, it can be removed. So finally, I think this is the final point which is arrived. So it is mathematics, we have to work out to understand still better. Okay. I'll also share this video so that you can listen to this video in your leisure hour and understand the simple mathematics behind the SVM algorithm. Now let us go to the hands-on session. So please give me 1 minute time. I'll switch on to my laptop because only in my laptop I have MATLAB. Is my voice audible? Kindly let me know whether my voice is audible. Hello. Yes. Okay. Thank you, ma'am. So now let me share the screen. Okay, now let me know whether the MATLAB screen is visible. Whether the MATLAB screen is visible. So here, what I'm going to do is just applying the SVM built-in function available in MATLAB and show you how the classification is done. Although regression is not there, I have not put. I'll do only for classification. You can work for regression as well. So first, what we have to do in MATLAB, there are some common commands like clear all and all, which will clear the workspace areas. First, all the data sets, whatever you have created, should be available in Excel. So when you want to use SVM in MATLAB for your application, what you do is you create the data set in Excel. Okay, you can have like one column as one feature. So automatically you will be having a matrix form data in the Excel, and you can save that Excel file as a .mat file. .mat file, that means matrix file. So once an Excel file is saved as a .mat file, here you can load. I will show you an example. Suppose if you have some variable like say this is your X matrix, okay. Session account. We are having a 10 samples, say one feature. Again, I'm putting random 10, 1. So assume that this column 1 is some current and column 2 is some voltage. Okay. So creating this is your X matrix. Once this data matrix is created, we are saving in a data file. So what I'm going to do is I'm going to save this X matrix in a sample.dat data file. Save it. Here you can see I'm able to get it, or you can even have a mat file, either as a data file or as a matrix file. I'll clear this. I'll save it as a mat file. Already one mat file is there. Let me clear that also. Okay, let me give some other name. So
Excuse me, ma'am.
Sample.
The screen is not moving. I think it is at standstill.
Oh my God.
So the screen is not updated.
Wait a minute. Whether the screen is visible or not. So,
No, ma'am. No, ma'am. No, ma'am.
I think there's a problem with network. Wait 1 minute. Okay. The screen is not coming. I don't know.
Yes, ma'am. Now it is visible.
No. Okay, okay. Sorry for the interruption. So what I have now, let me see whether the screen is moving. There is some delay communication. So what I have done here is just created on random data set X, and I have showed you how to save it. Later on, you can retrieve it. So there is a sample data set X which is created and it is saved in a file called sample new.mat. For saving, the syntax is save, file name, and the variable name. So the extension can give it just .mat. That is the preferred extension. Now I will clear all the variables in the workspace, and also I will put a clear screen. Once all the variables in the workspace is cleared and clear screen is also fine, here in the workspace there will be nothing. Here this is the workspace. For me it is visible. I think there will be some delay for you to see. Madam is telling, madam, please share full screen. Is the MATLAB screen visible now?
Yes, ma'am. It is visible.
Okay. So here, what I have done is I have saved a file called sample new mat. So load sample new .mat. If I give immediately, I will be able to retrieve the X data which I have saved. So today I am creating this. I am saving it, and tomorrow I can come and I can start working on it. Okay. So this is how the data set first need to be saved in the MATLAB file. So once the data set is saved, you can use any type of machine learning algorithm to train and test. So we are going to use the SVM toolbox in the MATLAB. There is a function called SVM train. So directly I will go to that. So before that, let me show you the help. Just by using help, you can learn everything in MATLAB. So I'm giving the only function which is used is SVM train and SVM classify. So it has a lot of mathematics about anything. Just the two major functions, SVM train and SVM classify, and used for the data classifications in this MATLAB toolbox. So here, you can see here, I'll just tell you what it is. So this is a command called load pressurize. So this is an illustration given directly in the SVM train. So fissurizes is a data set which is built in the MATLAB toolbox. So it is having 4 input attributes. It will classify the flower type based on the length, petal width, sepal length, and sepal width. Okay. So if I give only load fissurizes, these are all built-in data set available in the MATLAB. So if I just give load MEAS, which is input data, species is my output. Okay, I will clear this next. So means is my input and species is my output. So what is the size of means? If you see, size of means, it is 150 cross 4. That means this is your data set. 150 samples and 4 features. What is the size of species? It is 150 cross 1. So if you want to combine the species as a single one, mean is a numerical data and species is a text data, type data I will show you. So only it is not able to combine. First we have to this into numeric data. So species is like 3 class labels are there here. It's a multi-classification problem having 3 class labels: Setosa, versicolor, and Virginsina. So first 50 samples belonging to Setosa. This is just an example, okay? But in our real-time case, it will be like first 50 belonging to one class. Data sample 1 will belong to class 1, data sample 2 will belong to class 2. That doesn't matter. It can be random. No need to sort and all, okay? So what I'm going to do is, first I'm going to convert this cell data into numeric data. So there is a function in MATLAB called group to IDX, which will group all the names and label it. Okay, so all the setters has been given class 1, and the second flower type is class table 2, and the third one is class table 3. Now if I combine these two, I will store it in target. So now means and target is combined. So in order to visualize that, this is the complete. Here it is 150 cross 5. The last one is input. So for this particular input, your output class label. For this particular input, your class label is 1. So like that. Okay. So this is how the data set visualizes. Okay. Now once you will be able to get this means and species. What is the second? The second command, they are extracting only the first 2. I already told you that there are 4 attributes. First attribute is sepal width, petal length, and petal width. Five minutes, sir. Session முடிச்சிட்டாங்க. அட்டல் FDP ல இருக்கேன். Okay, so here it is. We are going to extract only because in order to understand application of SVM as a 2-dimensional problem, so we are having 4 features. I am taking only the first column and second column. So what this does is input matrix, the first column will be extracted. Input matrix, the second column. So automatically your X will be, instead of 1 cross 4, it will become 150 cross 2. Okay, so here if you put it will be 150 cross 2. Only the first feature and second feature is extracted. Then what you are doing is you are converting this into the species. So you are taking the first flower type, that is the class label 1. Extract this class. See what it does. So what it does is it is taking it as a binary classification problem. Although we have a multi-classification problem, it is taking it as a binary classification. So all the class label setosa is marked as true, and all the remaining 2 class label is marked as false. In order to convert the multi-class binary, this command does. I'm just showing you one by one command so that you will be able to understand. So first, the data set completely, then we are taking only the first 2 columns, considering a 2-dimensional problem. Then we are converting the multi-class SVM to binary class SVM by treating setosa as class label 1 and all the remaining as class label 2, that is true and false category. And then for the cross validation partition. So here what this cross validation does, y is nothing but your output. Okay, so it will hold out parameter which is given. If you want, we can put this in help and see what this basically does. So it uses, this is n target. K fold is folds you want to use 5-fold, 10-fold, something like that. The default value of k is 10. As I already mentioned, we can even go for 5-fold cross validation. So this CV partition means, for example, if you take a species, it will do the 10-fold cross validation. What is the meaning? That is, it will split the 150 samples into 10 sets, each set of 15 samples. And during the training process, it will take the first 15 as testing, the remaining 135 as training. In the second, it will second 15 as testing. So like that, 15 such test sets will be taken. So a single iteration itself, it will do 15 times, and finally for each and every case it will have an accuracy, it will take the average. That is what is the concept of cross validation. So that is what is done here. So here is given. So if it is 20% means if there are say 150 samples, you can assume 20% for training and remaining 80% for testing. I think 120 samples will be for training and remaining 30 will be for testing. So here we are a linear support vector mission. So classifier, I already mentioned that the only function we are going to use is SVM train. SVM train syntax is input, comma, output. That's all. Input is available in this P dot training. P is the matrix which has been partitioned. Okay, partitioned in the sense all computations will be there. First 20 testing and then remaining training. Like that, it will be going on. The first 30 testing and the remaining will be in the training. So like that, all computations will be there. So it is like a structure. So the all the training data will be taken and the P dot training corresponding output Y will be taken. For example, if we are having say 150 samples, we can take 120 for training. Say randomly I'm picking sample number 1, sample number 8, sample number 12. Corresponding output also should be correctly correct classifier. Suppose you are taking an input sample number 1, in output you are taking sample 2, misleading. So in order to avoid all those, you have to give, if it is P dot training, Y also should be P dot training. Okay. And then the next function is classify. So in class, we are giving testing data. So all this training and testing, where it will be, madam, if you ask, it will be inside this P. Inside the P, you'll be having training and testing. Just copy this, put it and put P dot training. You will be able to get the training and P dot test. So you can see size of P dot training. and size of so the entire testing for this particular case. Okay, but normally we should do like that. Since it is an example, it is taken like this. We have to manually split the samples into training and testing. I will show you. Okay, so now let me copy this and run it in order to show you how it works. So, SVM train and SVM classify. SVM train is used to train the model. Once the model is trained, subject the model to the testing set and see how much the classification is accurate. So here see, this is Tetosa, this is class level 1, all the remaining are class level 2. So 50 samples. Okay, and this is the optimal hyperplane separating because here we are converted a multi-classification into a binary classification problem. Error rate is 0, it means 0%, no, they're 100% accurate. So this is the confusion matrix. Among the 30 samples, all the samples have been correctly classified because in the half diagonal you have 0. 0 in the half diagonal means all the samples have been correctly classified and accuracy is 100%. So clear how this is working? Very simple. Using CV partition, you can manually split the training and testing. That is also. So if you want to have training samples, a train set, I can take random. So what I will do is I am generating numbers 1 to 150 one time. So each number will be repeated only one time. Stored in a variable called IDX. So in this, I am taking first 120 in training index and 121 to the last 150 is taking in the testing index. Okay, so randomly it is split up. So as a result, none of the training sample will be repeated in the testing or also. So those all the training index samples will be independent of the testing index samples. So now what I can do, I have the variable called mesh. So in mesh, I will select the training index samples. So that is called as X data. And similarly, this is X train data, or it as train data. And similarly, X data will be in the same input variable mesh. I'm going to take the corresponding test index samples with only first two attributes. So this is X test underscore data. Okay, so these are remember for splitting. Similarly, you have to do it for the target also, the corresponding output. So I'll take it as Y data and I will put here as target because I've converted the letters and all into number. I have to do it for binary classification. Similarly, Y test data. SVM basically in MATLAB, we can work for binary classification. If you want to explicitly write the algorithm. In order to avoid this, what I will do is the original I'm having 3 class labels, so it will show you. So I am converting into 2 class labels. That is what I'm doing here. So you can see true is taken as class label 2 and false is taken as 1. Okay. Now I can give y new of train data is equal to this y train data equal to y new of train index 1. And similarly, y test data will be equal to y new of train test index. So what I have done is I have the original x and y I have separated. Now I can apply SVM tree. SVM structure is the resultant output will be in the form of a structure. So SVM train of input comma out. Okay. So input is nothing but x train data. I think y train data. Let me see whether it works. Undefined function. Okay. I have instead of giving underscore, I gave comma. Yeah. Structure is built. So suppose here if you put show plot. Plot. So class.
Madam, am I audible? I think Madam got disconnected. So I thank you all for your patient listening. We will meet tomorrow morning at 9:30. Thank you all. Madam?
When I was disconnected, ma'am, I was not at all aware.
Last, only two more. That is, I think.
Whether that SVM train and class and all.
Yes, ma'am. You have presented all, ma'am.
I was just now only I went to the regular thing. It is telling that call is disconnected.
Yes. Now only you got disconnected. Don't worry, ma'am. Have you completed?
Yes, ma'am. I have completed. Actually, I was just telling about how to split the training and testing manually instead of
So that
using.
also we have listened.
Okay, then no, it's okay.
After that only you got disconnected. So no need to worry, ma'am.
Yes. Actually, I was
Yes,
using
thank you.
Wi-Fi because of that. College internet means no problem. There, MATLAB is not there in the system.
Okay. So network is very slow. Apart from that, since MATLAB is getting loaded, the system is getting slowed, I think.
Yes.
Yes, ma'am. Thank you for your wonderful presentation. Everyone is inspired by your presentation, ma'am. In spite of your busy schedule, you have spent a lot of time for us. You had an important meeting, so you missed that one for our sake. Thank you so much, ma'am.
Thank you, ma'am. Thank you.
Thank you for your presentation. I also learned a lot regarding SVM as well as how to use MATLAB for SVM. Thank you, ma'am. Thank you so much. On behalf of all the participants, I wholeheartedly thank you for your wonderful presentation. Thank you, ma'am.
Thank you all. If you have any doubts at any point of time, you can mail me. I will share my PPT and other supporting documents to the coordinator. You can get it and you can keep in touch with me if you have any doubts.
Okay, ma'am. I will definitely share. Please send your PPT and other materials. Many participants asked about the paper. Please send the papers also.
Sure.
I will share to the participants.
Sure.
Okay,
Thank you.
ma'am. Thank you. Thank you so much.
Thank you.